Let's see gravitational strength or intensity of gravitational field, which you also call gravitational acceleration. All these things are same. Strength of gravitational field, intensity of gravitational field, or acceleration due to gravity. It is represented by G. For Earth's surface, you already know its value. This is 9.8 meters per second square. We are interested in finding what basically G is. Look at this example. Suppose we have a mass m, and this mass m exerts a force of 10 newtons on another mass of 2 kg, which is placed at this point. This is the direction of force, and force is given as 10 newtons. So this m exerts a force of 10 newton on this 2 kg. But now, if I ask you that instead of 2, if I place 6 kg at the same position, if I place 6 kg at the same position with respect to m, then what will be the force on 6 kg placed at this point coming from capital M? Now, the steps which you will follow are like this. You will say that on 2 kg, force is 10 newtons. On 2 kg, force is what? 10. And therefore, on 1 kg, force is 10 by 2, which you will call what? 5 Newton per kg. On 2, force is 10. On 1 kg, force is what? 10 by 2, which is 5. If you place 6 kg at this point, then on 6 kg, force will be simply 5 into 6, which is coming as 30 newtons. This is the process which you are going to use for finding force on 6 kg if they are giving you force on 2 kg. But now look at the intermediate step, this one. This is what? Force on 1 kg, which is what? Unit mass. If you have information of force on unit mass, then you can find force on any other mass. You just need to what? Multiply it with that number. In this example, force on unit mass is coming what? 5. If I ask you that you place 8 kg, then what will be the force on that? You know that force on 1 kg is 5, and therefore force on 8 kg will be simply what? 8 into 5, 40 newtons. So this force on unit mass is something special for us. If we know it, we can easily find force on any other mass by simply multiplying that mass with this number. This number in gravitation is called strength of gravitational field or intensity of gravitational field, or something which you already know, gravitational acceleration. So this G, which you know as 9.8, is basically force on unit mass which Earth exerts at the surface. Let's say this marker, its mass is m. Now, what is g? G is force on unit mass near the surface of Earth. So force on unit mass near the surface, you say, is what? G. The way you remember G. And therefore, if I ask you that mass of this marker is m, what will be the force? We'll simply go and write what? Force on m, therefore is what? Mg. You already know that weight of this marker is what? Mg. So, what this G is? G is called force on a unit mass. Force on a unit mass gives you what? Strength of gravitational field. Strength of gravitational field at any given point in the space. We'll write the statement in formal way, but do one thing. First, note down this much elementary information. It tells you what G basically stands for, and then we'll write the whole statement in proper manner. Note down this much. Now look at the strength of gravitational field. Suppose we have a body of mass m. It's a body, random body. It can be a marker, it can be a sphere, it can be a point, it can be a ring. Due to this body, at this point P, we need to find strength of gravitational field. Strength of gravitational field at point P due to the mass body m. First, write down meaning of gravitational field. Write down the statement. Strength of gravitational field represents force on unit mass at any point in the space. At any point in the space. Gravitational field is a vector quantity. Gravitational field is a vector quantity. Its direction is always towards the gravitational force. Its direction is always towards the gravitational force. And its unit is Newton per kg or meters per second square. You understand everything? Look here. We need strength of gravitational field around this body at this point in the space, P. So, what is gravitational field? Force on a unit mass. But we don't have a unit mass. We had a mass m. This mass m is not a unit mass. It is some mass m. And we found that this mass body, capital M, exerts a force of F on it. Remember, this F is not gmm upon r square. That gmm upon r square is applicable when both bodies are point masses. This is not a point body, and therefore we have no idea what this force is. So, if force on this body is F, then you will say that on M, force is F. On M, force is F. Therefore, on unit mass, what is one? This one is your unit mass. On unit mass, force is F divided by M. This F divided by M is called strength of gravitational field at this point of the space around this mass body. Now, from this, first of all, you can see that unit of G is Newton per kg. Then you can see that what is acceleration? Force upon mass, and therefore unit of G is also meter per second square. The other thing which you can see is this. On M, force is what? F. What is force? A vector quantity. And therefore, on unit mass, force is what? F by M, which says that gravitational field strength is also a vector quantity. So, from this, you can also see that we can write F in the familiar form, which is what? mg. This is something you all know, that F is also written as what? mg. Now, what is G? Force on a unit mass. What does it mean when I say that? When I say that near this body, at this point, if somebody says that force on a unit mass is 5 newtons per kg. Suppose a notice type of is present here, and that notice reads this thing, that if you will place a unit mass at this point, then force on that point mass will be 5 newtons. That was the notice present here. You came, you removed the notice, and you said that at this point G is 5. That's what G means. Now, it gives you an easy way to calculate force. Once you have force on unit mass, you can calculate it for any mass. Now, to understand meaning of this, we'll take a simple example, and that simple example is what? We will find gravitational field strength of a point mass. Write down this. Find out gravitational field of a point mass. When I say gravitational field, it means strength of gravitational field, or intensity of gravitational field, or acceleration due to gravity. Find out gravitational field of a point mass at a distance r from it. This m is the point mass. And we need gravitational field of this point mass at a distance of r from it at this point P. This m is what? Now a point mass. This m is any random body. This is your point mass, and I asked you to find G at this point. What you did? You placed a point mass m. This m is also a point mass. This m is a point mass. If they both are point masses, then you know that we can easily write force as what? G m m divided by r square. This force is acting on m in this direction. That's direction of force. And once you have force on this end, what's the meaning of, and how do you find G? To find G, you simply write what? F divided by m. F divided by m. On m, this much force is present, and therefore on unit mass, what is the force? F divided by m. That F divided by m is called what? G. So what's F upon m coming from this? F upon m is coming G m divided by r square. This is the strength of gravitational field produced by a point mass capital M at some point in the space which is at a distance of r from it. What is the direction of G? What is G? First of all, remember, G is nothing but force. Force on unit mass. What is the direction of force? Towards the point mass. This M is pulling on this M in this direction. That is towards itself. And therefore, if I ask you what is the direction of gravitational field, what is the direction of gravitational field of a point mass? You will say that towards the point mass itself. Write down the statement. Write down the statement. Strength of gravitational field. Strength of gravitational field of a point mass. Strength of gravitational field of a point mass M, capital M, at a distance r from it, is Gm divided by r square, Gm divided by r square, and its direction is towards the point mass itself. And its direction is towards the point mass itself. And remember, this G is not 9.8. G, which you know as 9.8, is force on a unit mass when you place it near the surface of Earth. Let's take another example, which we already done. Write down the equation. Find out gravitational field. Find out gravitational field of a ring mass M. Find out gravitational field of a ring mass M on its axis at a distance of x from it. At a distance of x from it. This is your ring mass. If it's a ring mass, you know that you cannot use force as what? Gmm upon r square. And we have already done this article where we found force if you place a mass m on the axis of a circular ring, then force which acts on this mass, I hope you remember that this force is G m x upon r square plus x square to the power 3 by 2. Force on this point mass produced by this ring mass is given by this formula. But in the question we are asking what is strength of gravitational field at this point, which means I'm asking you, if you place a unit mass at this point, then what is the force on that unit mass coming from the ring? You know that. For that you will write G. What is G? G is force divided by M. F divided by M is coming gmx divided by r square plus x square to the power 3 by 2. So that was your random mass body. We have no idea what this force is, but when this random body it becomes a point mass, we know the force and therefore we can calculate what G. And G over point mass is coming what? Gm upon r square. When this mass body becomes a ring mass, again we know what a ring mass produces on the axis, what force it produces on the axis. Since we have that force, we can calculate strength of gravitational field on the axis. What is the direction of gravitational field on the axis? What is the direction of force? Towards the center of the ring. And therefore you will say that strength of gravitational field is gmx upon r square plus x square to the power 3 by 2, and its direction is towards the center of the ring. You will write like this, and its direction is towards the center of the ring. Put on this much. Let's find out gravitational field of Earth above and below the surface. Write down the heading. Gravitational field of Earth. Gravitational field of Earth above and below the surface of Earth. This is Earth. Its radius is r. Its mass is m. We need strength of gravitational field at this point. Height of this point from the surface of Earth is h. We need g at this point. Similarly, in the next part, we will find gravitational field at this point. This point is below the surface of Earth, again at some height h. So this is h, this is also h. We need gravitational field at this point, we need gravitational field at this point. Now, there are a few things which you must understand first before we start calculating G for Earth. If you have a hollow sphere of mass m and radius r, this radius is r and it's a hollow sphere. Then gravitational field strength at some point outside at distance r from the center. Remember, this r is taken from the center, but h is being taken from the surface. It's a hollow sphere. For a hollow sphere, if you need gravitational field outside, how do you define outside? Outside is defined this way. R is greater than or equals capital R. What is capital R? Radius. When you say R is greater than or equal to capital R, that means what? Equal means on the surface, greater means outside. If you are on the surface or outside, then you can consider all the mass of the hollow sphere at its center. All the mass of the hollow sphere at the center as a point. Now, once you say this mass can be assumed at the center as a point mass, then you know what gravitational field of a point mass is at a distance of r from it, and that is given by gm divided by r square. So this is gravitational field of a hollow sphere. If you are at this point, now what is this point? For this point, your distance from the center is r, but this r, remember, is r less than capital R. That means when you write r greater than capital R, you are outside or on the surface. And when you write r less than r, then you are inside the hollow sphere. Now, when you are inside at this point, G, strength of gravitational field, is what? Zero. What does it mean? If you place a unit mass inside a hollow sphere, then it will experience no force, because what is G? Force on unit mass. What is that coming? Zero. If you place a unit mass outside at this point, then that unit mass will experience a force as if whole mass of the hollow sphere is at its center. Now, you can develop these results if your maths is good. If somebody is interested, I'm giving you a hint. This is your hollow sphere. You can convert your hollow sphere into several coaxial rings. These are the rings which you place side by side, and then find out gravitational field. Find out gravitational field of these rings at this point. Due to first ring, what is gravitational field of a ring? Gmx upon r square plus x square to the power 3 by 2. So find out this x, find out the radius. Find out this x, find out the radius, and then find out gravitational field at this point and go for integration. Proper use of limits will produce G outside as Gm by r square, and when you go for inside points, you will find that G is coming what? Zero. It's not necessary that you go for it, but if you think that your maths is good, you can develop these integrations, then it's your wish, you can try for it. And if you find integration difficult, you're not able to complete that integration, you can always take help from my side. Now, but for any examination which we are interested in, we can simply use these results. Inside a hollow sphere, G is 0. Outside a hollow sphere, G is Gm by r square. Now, this is the hollow sphere, but Earth is not a hollow sphere. Earth is what? A solid sphere. If Earth is solid sphere, then how will you find gravitational field of a solid sphere outside? Let's go for outside point first. Now, what is outside? If you have a solid sphere, look at this solid sphere. Solid. Its mass is m. Its radius is r. We need gravitational field of a solid sphere at outside points. Now, this solid sphere is nothing but collection of several hollow spheres. If you have several concentric hollow spheres, just like an onion, different onion shells, collectively they make what? A solid onion. All these are what? Shells. Collectively it's what? An onion. Now, for these shells, let's say their masses are m1, m2, m3, m4, m5, m6. You have different radius for these, and you need gravitational field outside at this point r. We need at this point gravitational field for this solid sphere. Now, For the first hollow sphere, when you go for this point, you can see it is outside. And therefore, the first hollow sphere, you can have all its mass at the center. When you go for second hollow sphere, you can see that this point is again outside. And therefore, the second hollow sphere, you can replace all that mass of second hollow sphere with a point mass placed at the center. Now, keep on repeating this for all these hollow spherical shells because this point is outside of them. Once you say that all these spherical shells, their mass is centered at the center of the solid sphere, that means now at the center we have total mass of m. If total mass is m, then what is gravitational field of a point mass at a distance of r? At a distance of r, gravitational field is what? Gm by r square. That means if you have a solid sphere, then for the solid sphere, for outside points, that is r greater than or equal to capital R, gravitational field is simply Gm by r square. That means again, replace the whole mass of the solid sphere with a point mass and place that point mass at the center. Hopefully you understand that from this only we could develop this part. Now once we go for inside the solid sphere, you will understand this part in much better way, but even then it's not a difficult thing. Now once we found that a solid sphere of mass m and radius r outside produces this much gravitational field, then we can easily find gravitational field of Earth for the outside point. Look how we can find it. What is G at this point? G m divided by R. Now what is R? What is R? R is always taken from the center. So if you are interested in the outside part, for the outside part you can see that this is your R. This is your R. What is this R? This R is R plus H. And therefore gravitational field at height h above the surface of Earth is R plus h whole square. Now let's take R common, and once you take R common, it becomes Gm upon R square. Once you take R common, this is a square and therefore it is R square. Inside you've got 1 plus h upon r whole square. Now look at this number, Gm upon r square. If you are on the surface, that means you'll be using the equal sign. That means once you are on the surface of Earth, G is called G naught. This G naught is Gm divided by r square. What is G naught? Gravitational field on the surface of Earth, which you know as 9.8. It's not exactly 9.8, you will see it later, but right now G on the surface is what? Gm divided by r square. So this Gm by r square, you can replace it with what? G naught divided by 1 plus h divided by r whole square. This is G, strength of gravitational field at some height h from the surface of Earth in terms of G naught. What is G naught? Gravitational field, gravitational acceleration, intensity of gravitational field at the surface of Earth. Now, you have to remember this result. Apart from this result, we'll be using a second part also, and that second part is, if you say that you are interested in finding gravitational field at some height 100 meter, 500 meter, and this is 100, 500. What is R? 6,400 kilometers. So this is 100 meters and this is 6,400 kilometers. This number then becomes what? Very small. If this number is very small, then we go for a mathematical trick, and that mathematical trick is here. If somebody writes 1 plus x to the power n, then 1 plus x to the power n can be approximated with 1 plus n times x. You can approximate 1 plus x to the power n with 1 plus nx, not always, only if x is much smaller than 1. Remember this mathematical trick. 1 plus x to the power n is what? 1 plus nx, provided x is much smaller than what? 1. So, if I say that height is much smaller than r, height from the surface of Earth of that point where we need gravitational field is much smaller than the radius of Earth, then you can see that h upon r is also much smaller than what? 1. If this is much smaller than 1, then we can use this type of mathematical arrangement. This G is now G naught. Look here, 1 plus h upon r to the power minus 2. First, we have shifted this thing from the denominator to the numerator. Now, this is 1 plus x to the power n. And if h upon r is much smaller than 1, then you can always multiply the power inside. You can always multiply this power inside, and then it gives you G naught times 1 minus 2h divided by r. This is strength of gravitational field at some height h from the surface of Earth, provided h is much smaller than r. This is gravitational field at any height. This is only if h is much smaller than r. Note down this much. Now, let's see how we can find gravitational field strength inside a solid sphere. We have a solid sphere and we need gravitational field strength at some distance r from it, from the center. This is capital R. Total mass of the sphere is m. Now, what you can do is, you can say that the solid sphere is made up of these different colored shells. Let's say we have got blue shells and we have got black colored shells. It's a sphere. Now, this is the point where we need gravitational field. Mass of blue and black together is what? M. Now, what is gravitational field of a hollow sphere inside? You know that, 0. That means if I ask you what is gravitational field of this shell at this point, then you will say that it will have no gravitational strength at inside points. Same is with the other black shell and all the black shells which are outside of the point where we need gravitational strength. That means what we are saying is something like this. G is G, just for your understanding, G due to blue shells plus G due to black shells. Now if you go for black shells, then you know that black shells, they are not producing any gravitational field, and therefore gravitational field produced by the solid sphere at this point is nothing but gravitational field produced by the blue shells. That means you can say that this whole system, as far as gravitational strength is concerned, is equivalent to this. You can easily peel off these black layers. Even when you remove these layers, nothing changes as far as gravitational field strength is concerned at this point. But there is a slight change, and that change is what? Now, mass of this whole thing is only m dash. And what you are saying is gravitational field produced by the whole mass is same as gravitational field produced by m dash on its surface. Look at the wording which I am using, on the surface. Now what is it? The blue one. This blue is a solid sphere and we need its gravitational strength on the surface. And we just did this article only. What is gravitational field of a solid sphere on the surface? On the surface, that is we are finding G due to blue is G m dash divided by r square. What is m dash? Mass of all these blue shells. Let's use a simple argument. Mass of all these blue shells. For all these blue shells, you need gravitational field at outside point. If point is outside, then all these blue shells, their mass can be considered at the center. Now, what is total mass now at the center? M dash. Distance from the center of this point is what? R. And therefore, gravitational field is what? G m dash upon r square. The earlier argument which I gave you was that it is a solid sphere, but you need gravitational field inside. Once you remove these black layers, it is a solid sphere, and for this solid sphere, you are calculating gravitational field on the surface. If you need gravitational field on the surface, what is the formula? G, mass of the sphere, divided by radius square. G, mass of the sphere, divided by radius square. But we do not need m dash. We need our answer in terms of what? M. So, if I say that you have got an onion and you have peeled off these outer layers, if you have removed all these outer layers, then what is that which remains same? Mass? No. Volume? No. What is that? Density. So density is something which does not change. And if density doesn't change, then how do you write density? Mass upon volume. What is the original volume of the body? 4 by 3 pi r cube. Mass of the whole body is m. Its radius is r. But after removing black layers, we have got mass m dash and its volume is only 4 by 3 pi r cube. This gives us what? M dash. Your m dash is coming m 4 by 3 pi cancel, m into r cube divided by r cube. That's your m dash. If this is m dash, put this value of m dash in this. When you put this value of m dash in this part, it gives you what? G upon r square. What is m dash coming? M times r cube divided by r cube, which is G m r divided by G m r square r cube. That is r. That's your gravitational field strength inside a solid sphere. Remember it like this. This is the formula when r is less than r. When you are inside a solid sphere, gravitational field strength is given by gmr divided by r cube. Now, let's find out gravitational field of Earth. If we go for gravitational field of Earth for inside points, then what we can do is, this is Earth. We need gravitational field at a depth of h from the surface. From the center, this height is what? R. Depth is what? H. This is Earth. Of mass m. Now what is Earth? Earth is a solid sphere. We have gravitational field strength inside, but in terms of what? Small r. What is small r? Small r is distance from the center. This is the distance which is from the center. If center to this is r and depth is h, it's quite easy for you to see that small r in this case is nothing but r minus h. Capital R minus h, and therefore gravitational strength, gravitational acceleration, intensity of gravitational field at a depth of h from the surface of Earth is gm into small r, which is r minus h divided by r cube. This is what? This is coming. If you take r common, this becomes 1 minus h by r. And once you take r common, this r and r cube, they are cancelled and you are left with g m multiplied by 1 minus h upon r divided by r square. Now what is gm by r square? Gm by r square was gravitational field strength on the surface of Earth, and therefore this gm by r square, it is g naught, which gives us g as g naught gm by r square multiplied by 1 minus h divided by r. That's the formula without any approximation. For points above the surface of Earth, we have two formats. If you are below the surface of Earth, you just need to remember g as what? G naught times 1 minus h upon r. What is G naught? Strength of gravitational field at the surface of Earth. Note down everything.